Hello, in this video I'm going to continue working on the code refactoring that I created in the previous video. And in the previous video, we created a code refactoring that converts action or func parameters into custom delegates, right? So here in this unit test, we have a method taking an action or string parameter, and when the user refactors this parameter, the refactoring would create a new delegate based on the action and then use it in the method. And in this video I'm going to continue working on this code refactoring to support more scenarios. Okay, so first I'm going to do some refactoring. I'm going to rename this testing class here, and I'm going to extract this part of the test into its own method so I can reuse it. Okay, and let me rename this test method. Okay, let me copy this test. So in this test, I'm going to assume that there's another class in another document that calls this method here. Let me show you. Okay, so here we have another class that I'm going to put in another document that has a method called method2 with a similar action parameter, and then this method2 will call class1.method1 passing this right parameter. Okay. So here I expect the caller code to change, and the change would be in the type of the right parameter. I want this parameter to have the type class1.write, which is the newly created delegate, right? So now I need to update this apply code refactoring method so that it allows me to have another document in the project. Okay. Okay, so here I'm creating a new document ID for the project, and then I'm adding the new document using this parameter as the source code. Here we are returning the updated text for the first document, right? We need to do the same thing for the second document. Okay, I need to fix the return type of the method now. Okay, and I'm going to create an overload of this method that doesn't deal with the second document so that the first test compiles. Okay, and here in the second test where we are interested in the second document, I'm going to use the overload of apply code refactoring that deals with the second document. And here I assert that the caller document was updated in the way that I want it to be updated. Okay, let's run the test now. Okay, and the test failed because we expected the caller method to be updated, but it didn't update. Okay, now we are ready to work on the code refactoring itself. Okay, before I continue, I'm going to do some refactoring. So here, I extracted the code that creates the delegate into its own method. and this method returns the delegate declaration and the delegate name as out parameters. So next, I'm going to find all parameters in the solution that are passed as values for the parameter that we are refactoring. For example, in this test, this is the parameter that we are refactoring, and this is an example of a parameter that I want to find, because the value of this parameter is passed as an argument for this parameter, right? Okay. Okay. So this method, which I will be implementing next, we will give it a parameter and the solution, and it will find all parameters in the solution that will be used as arguments to this parameter here. Okay. And when we return each parameter, we also return the document that contains this parameter. And we want a reference to this document so that we update it to change the type of the parameter, right? Okay. Okay, so here I'm getting the method that contains the parameter, right? And then I'm using a method called findCallersAsync to find all callers of this method, right? And this method returns a collection of simple caller info objects, right? And because this is a collection of simple caller info objects, one might think that each item in this collection represents an invocation of the method, but this is not the case. Instead, each symbol caller info object represents a set of invocations, and the invocations in a single set have things in common. For example, if we have two invocations to the method coming from two different methods, then these invocations will belong into two different symbol caller info objects. Let me show you the definition of this object. So this object has a property called calling symbol, and this will contain the symbol of the calling method, right? And then there's a property called locations, and these will be the locations inside this symbol where our method is called, right? And this called symbol property will be our method, right? The one we pass to findCallersAsync, right? And the reason we have this property here is that sometimes the value of this property is not exactly the same method that we gave to the findCallersAsync method, right? And let me give you an example. Let's say that we have a method in a class that is also part of an interface implementation, and there are two callers to this method, one using the concrete class that contains the method and one using the interface. In this case, findCallersAsync will create two symbol caller info objects, and the called symbol in these two objects will be different. One will be the concrete method inside the concrete class, and one will be the method in the interface, right? So basically we can think of this as a grouping of invocations based on things like the calling symbol and the called symbol. Okay. Now here what I'm doing, I'm going through all invocation sets and accessing the locations property, right? This will give me all the locations of invocations, right? And then for each location, I'm getting the document of that location, and then I'm accessing the root node of that document, and then I'm getting the node represented by that location. Now in the case of our test, this node will be an identifier name syntax, right? The parent of that node will be a member access expression, and the parent of that will be an invocation expression. So this is the node that will be returned by the findNode method when we give it the span of the location, right? This will be the member access expression, and this will be the invocation expression. Now this code is not very reliable, and I will show you cases where this code will not work, but since I'm doing test-driven development, this code will work for now. And here I'm returning the invocation and the document that contains the invocation. Okay. Okay. So now these invocations represent calls to the method, right? And here I'm looping through these invocations, and in this line I'm trying to find the argument that is passed as a value for the parameter, right? And here I'm using the index of the parameter in the called method as a way to know which argument to get from the list of arguments in the calling side, right? And this code is not very reliable because if the code contains named arguments, the argument index at the calling side wouldn't necessarily match the parameter index of the method itself, right? But since we're doing test-driven development, this should work for now. Okay, here I'm getting the semantic model of the document that contains the invocation, and here I'm checking to see if the argument passed to the method is itself a parameter, right? And if it is, I'm adding it to the result list here, right? Okay. So this variable here will contain the parameters of caller methods that are used as values for our parameter, right? And for each parameter, we also have access to the document that contains this parameter. Okay. So what I'm going to do next, I'm going to loop through all these parameters and change their types from action or func to our newly created delegate, right? And to remind you, here, when we change the types of these parameters, we should use not only the delegate name, but also the class that contains the delegate, right? So it should be the class dot the delegate name. Okay. Okay. So here what I'm doing, I'm creating a qualified name syntax to represent the full delegate type, right? And this corresponds here to this piece of code, right? And in order to do that, we need to get the name of the type that contains the delegate. Here we have the type as a type declaration syntax, and here I'm using the semantic model to get the containing type as a symbol using the getDeclaredSymbol method. And this getDeclaredSymbol method, you give it a syntax node that represents some declaration of a symbol, and it gives you back a symbol, right? And I need this symbol here because I want to use the syntax generator class to help me create a type expression to represent that type, right? So in the case of our test, this will create this type syntax here, but that code is useful because if this class, this one here, is a nested class, then the syntax generator would generate syntax representing the full class name, right? Okay. So here this will contain syntax that represents the containing type, and then I append the delegate name as a member of this type here using the syntaxFactory.qualifiedName method, right? So this will represent the complete type of the delegate, right? So here, after calling the findSourceParameters method to get all the parameters in caller methods that are passed as values for the parameter that we want to refactor, I'm looping through all these parameters, and then for each parameter I'm getting the document of the caller, the root node of that document, and then here I'm getting the parameter syntax node that represents the parameter in the caller document, right? And to do that, from the parameter symbol, I'm getting the locations of that parameter symbol, right? And I expect there to be only a single location because a parameter in a method has a single location. And then I'm getting the source span of that location, right? And using this span, I'm using the findNode method to find the node on that span, right? Now here it might be confusing why there's a locations property and not location. And the reason is that some symbols have multiple locations. For example, for partial classes, as far as the semantic model is concerned, there's only one symbol, right? But as far as the syntax is concerned, you have two class declaration syntaxes, right? Or maybe more, right? Now once I have the parameter syntax in the caller document, I update its type to be the delegate type, right? And then I'm creating an updated root node for the caller document that contains the updated parameter syntax, right? And then here I'm creating a variable called solution that contains the current solution, right? But then I'm updating the solution to contain a new root node for the caller document, right? Okay. Now here we used to return an updated document, right? But here, because the refactoring now might update multiple documents, we are updating the solution to change the root node of the document, which contains the parameter we want to refactor, to be this updated root here, right? Okay, and here we return the updated solution. And I had to change the return type of this method to be task of solution instead of task of document. And this worked just fine because this create method here has two overloads. One expecting us to return a modified document and one that expects us to return a modified solution. Okay, now let's run the test. Okay, great. The test passes. Okay. Let's create another test now where we also have a caller in the same document that contains the parameter that we want to refactor. Let me show you. Okay. So here I added a new method to the same class that contains the parameter that we want to refactor, and this method calls this method here, right? So here in the expected updated code, we expect the type of this parameter to be changed to the delegate name, right? Okay, let's run the test. Okay, and it fails. And it says here sequence contains more than one element. And this is actually a problem in the test itself, and let me show you. So here in the apply code refactoring method, we are expecting to find only a single parameter declared in the document. And because we have defined two methods and each of the methods has a parameter, the call to single here fails, right? So I'm going to use first instead of single. And this means that the parameter we want to refactor is the first parameter in the document. So for example here, the test will consider this parameter to be the parameter that we want to refactor. Okay, let's run the test now. And here we have an invalid cast exception, and it says unable to cast object of type expression statement syntax to type invocation expression syntax. Let's debug the test to see why this is happening. Okay. So before I said this piece of code is not reliable, and this is an example of why. So this code tries to find the invocation expression of the caller, and originally when I wrote this code I expected the parent to be a member access expression and the parent of the parent to be an invocation expression, right? But here the parent itself is an invocation expression, and let me explain to you why. So for the second caller here, the parent is a member access expression because here we are in another class. We have to have a member access expression here, right? We have to specify the class name and then dot and then the method name, right? Now in this caller, because we are in the same class, I didn't have to specify class 1 here, right? I didn't have to do this, right? So if I do this, I will not get this exception, but I want also to make it work for code that accesses the method like this, right? Okay. Okay, so this solution here will handle the two cases, right? And because we are doing test-driven development, we will handle more cases as they arise. Let's run the test now. Okay. So here in the actual code, we see that the type of this parameter was not changed, right? And let me tell you why. So here what we are doing is we are finding the callers of the method, right? And then we are updating the callers here, right? And because in this test we have a caller in the same document as the parameter that we want to refactor, here we are making changes to that document, right? But then here when we want to add the new delegate and update the method that contains the parameter that we want to refactor, we are using syntax nodes from the old solution, right? That is, here we are updating the solution, but the nodes here are from the old solution, right? So basically what ends up happening is that the changes we made here to the document are lost when we make these changes, right? And there are multiple ways to fix this. Let me show you one. So currently I'm processing callers before I create the delegate and process the method itself, right? So what I'm going to do instead, I'm going to make these changes here and then process the callers. There is more that I have to do then, but let me show you first what happens if I just do that. Okay. So now I'm creating the delegate and updating the method, and after that I'm handling the callers, right? So let me run the test just to show you what happens. So the test still fails, and let's see the actual updated code. So here the caller method was updated correctly, but the delegate was not created here, and the type of the parameter that we want to refactor was not changed. So basically these changes here were overridden by the changes we did here, right? So this is the opposite of the effect that we had before, right? And the reason this is happening is the same as before. Here when we find callers, we are using the old solution, and therefore the documents we get here are the old documents, right? And therefore when we update the solution here, this updated root node here will simply be the original document having only these changes, right? Ignoring any changes that are done here. Okay. So to fix this, let's use this updated solution here instead of the old solution, right? So let's run the test and see if this fixes the issue. So it didn't. So here, the delegate was added and the type of the parameter that we want to refactor was changed, but then the caller method was not updated correctly, right? And the reason this is happening is that this parameter symbol is part of a compilation that belongs to the project in the old solution, right? Not this one. So basically, if we debug this code here, this method will return an empty array. Let me show you. So the array is empty. Okay. Now to fix the problem, we need to find the parameter symbol that corresponds to the same parameter but in the new solution. Let me show you how to do that. So this is the code that updates the method to change the parameter type from func or action to the delegate type, right? So what I'm going to do, I'm going to annotate the parameter syntax node with a special annotation, and I will explain what that means. Okay. So here when I update the method, I'm replacing the parameter syntax node with an updated version of that node that has the type changed as before to make the parameter type be the new delegate, but then I'm using this with additional annotations method to basically tag this parameter syntax node. So once we annotate a syntax node with some annotation, we can search for that node using this annotation. So basically I can do something like this. So this allows me to search for the parameter inside the method, right? And then when we update the root node to replace the method node with the updated method node, I can also search for the annotated node from the root node, right? But not only that. The interesting thing about annotations is that they survive changes to the document. For example, here once we make the changes and then the solution is updated, we can use that annotation to find the parameter syntax in the new document, right? And let me show you why this is important. So syntax nodes are immutable, right? And because using a node we can get any other node in the same tree, when one node changes, that is, when we create an updated version of one node, all nodes in the same tree have to change. For example here, when we change the members of the containing type, a completely different tree will be created, right? And as I said before, this is true because you should be able to traverse the whole tree from a single node, right? So this is very important. Let me explain this to you with some images. So here I have one tree, right? Let's say that I want to update one node, right? This one here, okay? Because nodes are immutable, we create copies of nodes, right? So basically this node here is a copy of this one here, but then I'm going to color it red to say that it was changed, right? Now what happens, this node, the parent of this node, can't be the exact copy of this one here, right? And the reason is you can navigate from this parent node to this node using some properties, right? And when you use this node to get the child node, you should get the updated child node here. But from here, when you get the child node, you should get this node here, which is different, right? This is why when changing only one node in the tree, copies of all nodes have to be created, right? Because once you change this parent node here, you have to also change this one, right? And then you have to change this one, and this one, and this one, and this one. So basically, whenever one node changes in the tree, a copy of the whole tree is created. Now that doesn't mean that there isn't some performance optimization. There is, but I'm not going to talk about that. Now the interesting thing is that if you annotate a node here, and then you update this node here, the copied version of this node here will contain the exact same annotation. And this is why I think annotations are very helpful. They are a way for us to track nodes. Okay. So now we have the annotation ready. Let's use it to find the parameter syntax node in the new document. Okay, so here I obtained the updated document and then the semantic model for that document, the root node for that document, and using the getAnnotedNodes method, I'm able to find the parameter syntax node that corresponds to the original parameter syntax node, right? And here I'm using the new semantic model to get the symbol for the new parameter syntax. And now here I can use the new symbol, and this will work because this new symbol belongs to this solution, right? Okay, let's now run the test. So the test failed, and let's look at the actual updated code. So here the delegate is created correctly, and the parameter type is changed correctly. And for the caller, the change was done, but here the full qualified name is used, right? But in the test, because the caller is in the same class, we expected only the delegate name to be used, which is right? Okay, so it seems we need to distinguish between callers from the same class and callers from outside the class, right? Okay, let's go back to the code. So here for the callers, we are always using the qualified delegate type, right? So let's fix this. Okay, so here for the new parameter type for the caller methods, we check to see if the caller is in the same document, right? If it is in the same document, we just use the delegate name as the type. Otherwise, we use the qualified delegate type, which includes the class name, right? And this code, by the way, is not reliable, because what if there's another caller in the same document but in a different class, right? But this will do for now to make the test pass. Okay, so the test passed, great. Let's run all tests. Okay, great. Okay, so let's see the new behavior in action. So this code is similar to the unit test. Here we have the main method that calls test2, and test2 calls test1. And here I'm going to refactor this parameter in test1. Okay, so the delegate was created and the parameter type was changed, but the parameter type of the caller wasn't changed, right? And this is unexpected. So I did some troubleshooting of camera, and I started by creating a unit test that contains this exact text here, and the unit test passed. So it seems that the behavior of the code refactoring is different between a unit test and a real Visual Studio environment. And I did some further investigation, and the problem seems to be with a new Visual Studio feature, which moves some of the Roslyn processing out of process. And I found a workaround. Let me show you. Okay. So here, after we add the new delegate, I'm going to call a method called normalize whitespace. So when we manually create syntax, that syntax wouldn't contain trivia like white spaces between the keywords, right? Now this normalize whitespace method, it creates whitespace trivia between the nodes. I'm not going to talk about this method in details, but you can think of this method as a way to somewhat format the syntax. And it seems that this out-of-process feature of Visual Studio doesn't work perfectly without this. So let me run now. Okay, let me refactor this parameter. Okay, and it's working now. Okay, so there's more to this issue for me to understand, and I might talk about it in a new video. Okay, thank you for watching.